These are notes on percent composition, empirical, and molecular formula. And for those of you who think that this is a typo, the official plural of formula is formulae with an E on the end, not an S, even though your book doesn't do that. And this is section 10.3 in your book. So for those of you who like to follow along, I suggest getting your book out now. We're going to be talking about how we figure out what formula of a compound we have. So percent composition is the percent by mass of the elements in a compound. And it's pretty straightforward if you think about what that means. Like, for example, in H2O, what percent is hydrogen, what percent is oxygen? What's a little complex is that, somebody may look at H2O and say, well, H2O, 2 parts hydrogen, 1 part oxygen, so it's got to be about 2/3 hydrogen and 1/3 oxygen. Well, that's not necessarily the case because we're talking about the percent by mass. And hydrogen has a really small mass, 1.00 grams per mole, compared to oxygen, which is about 16 grams per mole. And so even though there's 2 hydrogens to every 1 oxygen, by mass, the hydrogen makes up such a small percent. So the mass percent of an element is the total mass of the element, meaning, for example, if it's H2, then you're going to multiply that by 2, divided by the mass of the compound, and then times 100%. Just like in percent error, we multiply by 100% in the end. And percent is more of a unit. So keep that in mind. You don't multiply by 0.1. It's actually multiplied by 100. So the mass percents of each element in the compound then must total 100%. So just like anything else, if you're looking at percents of a total of anything, all of the parts need to add up to 100%. So what is the mass percent of potassium in potassium sulfate? And I put in here that potassium sulfate is K2SO4, just so you don't have to stumble upon what's the formula. But if you don't understand kind of intrinsically why it's K2SO4, I would go back and relook at that, because here again you see that knowing the correct formula is going to lead you to the right answer. Thinking that the formula is something different, KSO4 or KSO3 or anything else, PSO4, is going to end up pulling you down the wrong road. And if you start off on the wrong path, you're going to end up on the wrong path in the end. So go ahead and try to figure this out based on the equation above. Pause the video and then check your answer. So the mass percent of potassium is 2 times 39.098, and that's 2 potassiums, divided by 2 times 39.098 plus 32.06, that's the sulfur, plus 4 times 15.9994, that's the oxygen, times 100%. So if you didn't even get that, now at least try it on your calculator. Make sure you can use the calculator properly. And that gives you 44.87%. So then go ahead and calculate what's the mass percent of the sulfur, what's the mass percent of the oxygen. And once you get to the oxygen, having calculated the sulfur, you should be able to add the potassium and the sulfur and subtract that total from 100. But if you didn't get this first one with the potassium, I would recommend going through and calculating it as if you didn't have a shortcut, just to make sure you know how. And you should have found that the mass percent of the sulfur is 18.40%, and the mass percent of the oxygen is 36.73%. By the way, these 4 sig figs are stemming from the mass of the sulfur right here, which is 32.06, and that's 4 sig figs, and that's the least number of significant figures in this entire thing. And so that's what's going to drive our significant figures. And if you add up 44.87 plus 18.40 plus 36.73, you do find it comes out as, as 100%. All right, so we can also use percent composition to find unknowns. So for example, what is the percent composition of the compound formed when 2.70 grams of aluminum combine with oxygen to form 5.10 grams of aluminum oxide? So in this case, you could absolutely go and find the formula of aluminum oxide and then do mass percent like you did in the previous question. But you actually don't have to go into that kind of depth here, and it makes it a lot easier. And I know you guys are always looking for easier ways to do things. So if we know that the total mass of the aluminum oxide is 5.1 grams, and we know we use 2.7 grams of aluminum, then we know that the oxygen must be 5.10 grams minus 2.7 grams, which gives you 2.40 grams of oxygen. So now we have the total mass, which is 5.10 grams, and then we have the mass of each aluminum and oxygen. So go ahead and solve this, and then again, check your work. So you should have found that the mass percent of aluminum was 52.9%. That comes from the 2.70 divided by 5.10 times 100%. And that the mass percent of the oxygen is 2.40 divided by 5.10 times 100%, which is 47.1%. And here again, one of the things, and this is what I was talking about before, is that the aluminum, even though there's fewer aluminums, it actually makes up a greater percent because the mass of aluminum is more than the mass of oxygen. And so kind of keep that in mind. And if you want to do a double check, now would be a great time to pause the video and find out if I had just said, what is the mass percent of aluminum and oxygen in aluminum oxide. You can go through and calculate that based on the periodic table, and you should find that it is 52.9% and 47.1%. So now we're going to look at empirical and molecular formulae. And the word molecular shouldn't be new to you. We've been talking about that a lot. But empirical maybe. So the empirical formula shows the smallest whole number ratio of elements in a compound. The molecular formula shows the actual number of atoms, and it should say in a compound, not on a compound. We're not going to change that now, but in a compound. So, and we can use molecular and empirical formula even for ionic compounds. So normally we would say molecules are just covalent, but we could use it for ionic as well. And then when we're talking about the molecular formula, that would be, it would talk about the smallest, it would be talking about a formula unit, one formula unit of the compound. So let's look at what the difference between those is. So let's take two molecular formulae. We're going to take C2H2, which is ethine. It's a gas. It's used in welders' torches. Then we're going to take C8H8, which is styrene, which is a component in polystyrene, which is what those little packing peanuts that you get, in packages that get sent to you, and it's very delicate. So that's styrene. And so if you look at those, they clearly have different molecular formulae. Ethine is C2H2 and styrene is C8H8, and they have different properties and they're different compounds. But if you notice, they both have what would be called the same empirical formula. The empirical formula, which is the smallest whole number ratio, it's almost like taking a fraction and reducing it to the smallest, I don't remember what it's called, but reducing it so that you can't reduce it anymore. Whatever that's called. C2H2, you could divide both by 2 and you get CH. Styrene, C8H8, you can divide both by 8 and you get CH. So the empirical formula for both of these is CH. So they have the same empirical formula, but different molecular formulae. And I'm going to show you how these two are useful with one another, and then we'll actually go through and figure out how you calculate these. So the molecular formula is the empirical formula multiplied by a whole number, which could be 1. There are times when the molecular formula and the empirical formula are the exact same formula. So H2O, for example, The empirical formula is H2O. There is no way to reduce the 2 and the 1. And the molecular formula is H2O. In the case of ethine, the molecular formula is CH multiplied by 2. And in the case of styrene, it's CH multiplied by 8. And so you can see in each case we're multiplying the empirical formula by a whole number. And the molecular formula and empirical formula and this quote-unquote magic whole number are related mathematically. The mass of the molecular formula divided by the mass of the empirical formula equals the whole number multiple, whatever that magic multiply number is. And that makes sense, that if we think about ethine, for example, whatever the mass of C plus H is, ethine, which is C2H2, is going to be twice that. So then I actually went through and figured out styrene for you. So styrene, which is CH88, is 8 times 12.011. That's the mass of carbon, plus 8 times 1.008, which is the mass of hydrogen, divided by 12.011 plus 1.008, and that number ends up being 8. And that's pretty obvious here because we've multiplied both by 8, and so obviously the answer is 8. A lot of times what you'll have, though, is an experimentally determined molecular mass. So whatever that number is, 8 times 12 is, oh boy, like 96, plus 8 is going to be about 104. So you might get something that says, the molecular mass was experimentally determined to be 104 grams per mole. And then you could calculate the empirical formula mass, and then you would divide and get 8. All right, so how do we determine the empirical formula? And this is in 10.3, especially if you feel like you're struggling at this point. I would really have this open. I might even read through 10.3 first, look at the examples, and then come back to the video. It certainly is your choice, but that would be my recommendation if you're struggling. If you're not, if you're like, yep, I'm getting all this, math is really my thing, then I think you can kind of press on. So let's take this problem. Calculate the empirical formula of the compound that is 40.0% carbon, 6.7% hydrogen, and 53.3% oxygen. So certainly those of you who are mathematically inclined and have not read the book, you're welcome to kind of jump in and see if you can figure out how you might start this and where you might go from there. If that seems like too big a job, I've sort of broken it down, so at any point you can just stop and say, okay, I think I've got it from here, I think I can go from here. So remember that the percents are percents by mass. And so the first step we would do is, let's assume that we have 100 grams of the substance. If we have 100 grams of the substance, then 40.0 grams of that is carbon, 6.7 grams of that is hydrogen, and 53.3 grams of that is oxygen. Now, that's definitely helpful, but not helpful enough, because remember, a formula, when we're talking about a formula, again, like H2O, we're talking about moles, right? In 1 mole of H2O, we have 2 moles of hydrogen and 1 mole of oxygen. So to get those numbers, we need moles. Luckily, we know how to convert grams to moles. So let's go through and convert grams of each of these to moles of each of these. So you can go ahead and do that. You can pause the video, and then you can check your answer. So first, we've got carbon. So 40.0 grams of carbon times 1 mole of carbon over 12.011 grams of carbon gives us 3.30 moles of carbon. So hopefully that's what everybody got. It's a very basic conversion, but it's one of those that you absolutely have to know how to do in order to move forward. So then here we have the conversion from the 6.7 grams of hydrogen and the 53.3 grams of oxygen. So we end up with 3.30 moles of carbon, 6.6 moles of hydrogen, and 3.33 moles of oxygen. And at this point I've run out of space, so I'm going to go on to my next slide, but we'll come back to this data. So, whoops. Well, there's our answer, but that's my mistake. Let's go through and figure out how we would get this. So let's take that idea again. We've got 3.3 moles of carbon, 6.6 moles of hydrogen, and 3.33 moles of oxygen. So realistically, our empirical formula, and I should have put that in quotes because the empirical formula is the smallest whole number ratio. But what this means is that whatever ratio we have, it's C 3.30, H 6.6, O 3.33. But the empirical formula is in fact the smallest whole number ratio. So in order to do that, we're going to divide each of these number of moles by the smallest number. So the smallest number is 3.30. So dividing each molar amount by the smallest number of moles, which is 3.30, gives C 3.30 over 3.30, H 6.6 over 3.30, O 3.3 over 3.30. We're essentially reducing here, and that gives us CH2O. One thing to note is in this example, it came out very nicely with a 1-to-1 ratio. Sometimes you end up with something like 1, 2.5, and 1. And so what you then need to do is multiply by a small number to get whole numbers even after you divide. So what I would do is, in order to see that, there's a great example of that in your book. It's sample problem 10.11. I would maybe try to figure it out all the way to the point that we got to here, and then it shows you, because I think there's like a 2.5 or a 2.33 or something, how to multiply to get whole numbers even after you divide. So then we can link the molecular formula to the empirical formula. So we already talked mathematically about how that works. So if you remember, the mass of the molecular formula divided by the mass of the empirical formula equals a whole number multiple. So that's from a couple of slides ago. Hopefully you remember that. So let's take this example. What is the molecular formula of a compound with the empirical formula CClN, so carbon, chlorine, and nitrogen, with a 1-to-1-to-1 ratio in the empirical formula, and a molar mass of 184.5 grams per mole? So how do you get a molar mass if you don't know what the molecular formula is? The answer is it's experimentally determined. And in fact, empirical formulas are experimentally determined. So usually what's used is a device called a mass spectrometer, which then gives you mass percents, and you can calculate the molecular mass from that. If you watch any of the crime solving shows like Bones or anything like that, they're always running things through the mass spectrometer. So that's how we get our experimentally determined molecular mass. Okay, so remembering that that whole number multiple is the molecular mass divided by the empirical mass, we have the molecular mass. We can calculate the empirical mass because that's 1 carbon, 1 chlorine, and 1 nitrogen, and then we can divide. So the empirical formula mass would be 12.011, that's the 1 carbon, 35.453, that's the 1 chlorine, 14.007, that's the 1 nitrogen, which equals 61.471. So then we get the 184.5 grams per mole, which was given to us, divided by 61.471 grams per mole, and that equals 3.001. Now looking at this number, we're not going to multiply by 3.001. We're simply going to multiply by 3. Remembering that these are experimentally determined, sometimes we end up with some really small decimal like 0.001, and we're just going to assume that in nature that ratio is actually 3. So we're not going to worry about that. Similarly, in some of the examples you'll do, you might get a something that's like 5.999. We're going to assume that's 6. and that it's not some weird funky ratio. So 3 times CClN is C3, Cl3, That would be our molecular formula from our empirical formula. So go ahead and do this problem. What is the molecular formula of a compound that is 58.8% carbon, 9.8% hydrogen, 31.4% oxygen, and has a molar mass of 204 grams per mole? Then, once you figured that out, what about a compound with the same empirical formula, but a molar mass of 102 grams per mole? So figure both of those out, and we're going to talk about them tomorrow in class. Please make sure to put any questions you have on the comment section of YouTube or email them to me. Or simply ask your classmates, since most of you are doing this in class. Have a good day.